Hello everyone, welcome to AI Everyday Virtual Bootcamp Season 2. Alright, so before we get started, I would love to introduce Data Science Nigeria. Data Science Nigeria is a registered non-profit organization with the aim of building a world-class AI ecosystem driven by research and innovation. And part of our plan is to reach out to millions of talents, AI talents in 10 years. And part of the things we've been able to do for over 2 years and counting right now is we've been able to have we have over a million downloads of our artificial intelligence for startup free ebook, which we had contributions from AI experts like Professor Elisha, Professor Emeritus Thomas Detrick, and Professor Welling. And then we've also had over 10,000 participants who participated in our first ever international competition. We've had over 12,000 online participants in data science courses, at least those who took at least a class in data science. We've had over 2,000 hours of free classes on data science and machine learning in different states in Nigeria. And we've also been able to share out 2 terabytes hard disk that contains over 10,000 publicly available AI learning videos across our cities and campuses, across 72 cities and campuses. All right, so we've been able to reach out to 310 people that are community members today who have benefited from our job placements, project participation, and internship opportunities. We've had over 48 people who are research students who have been supported and mentored in their masters and PhD. We've been able to reach out to 30 cities where we conducted free introductory machine learning class and data science, and we had over 5,000 students from those 30 cities who participated. We've been able to have 4 innovative product ideas. All right, so we are so humbled to run the biggest AI learning program in Africa with 29 unique platforms. So our programs are either face-to-face, online, offline contents, and hands-on programs. And then the segments of our programs are always beginners, kids for teens, intermediate to experts, higher institution students, and then professional C-level executives. For example, for the professionals, in our face-to-face programs for them, we've had the business analytics for professionals. Alright, so before we go into today's class, let's hear from some of our attendees of our paid training.
Okay, so I chose data science because, it's the future.
The vision of DSN, I identify with it. It's something I can relate with. The vision of wanting to create a hub for data scientists in West Africa. It's something that is highly needed.
Yeah, so far so good. Has been a wonderful one. I was able to learn the use of data to interpret data, to predict the future, definitely.
My big take home is probably sentiment analysis and then the use of big ML.
Today we did data visualization, dealt extensively with Power BI. There's a whole lot I can do with it. Things that we've been trying to analyze, I can now visualize it and it will make more sense to my audience.
Big ML majorly, it has been my own major takeaway, and the lectures were so broken down such that anybody can understand it.
So what Sheon told me is lesser than what I even experienced there. The facilitators, they took us like children. It was like a dummy taking the course.
Tell everybody I come in contact with, especially young people in school right now, jobs as we know it will no longer exist. So you should get trained, in one of the technical skills. It could be data science, machine learning, artificial intelligence. That is the future.
So for me, DSN, the vision, is something that every forward-looking Nigerian should identify with.
Yeah. As you can see, that was highly insightful. A lot of them had awesome experience with us. Yeah, okay, let's move on. So you can actually visit this link to learn more about our trainings. Yeah. Alright, so let's get started with our class on TensorFlow for beginners. I am Odemakinde Elisha, Tofunmi. Alright, so I work at Data Science Nigeria as a data scientist and as an AI researcher. So this is my Twitter handle, Medium. So I write articles on Medium related to AI, data science, machine learning. Check it out to read more. So there's my GitHub profile, my GitHub username, then my email. You can reach out to me via this email. Alright, so these are the things you're actually going to be looking into. What next? TensorFlow prerequisites, introduction to TensorFlow, setting up TensorFlow operations, neural networks with TensorFlow, and we'll be considering losses, optimizers, activation functions, and others. So we're also going to be putting all of these things, the things we've learned from TensorFlow, into developing a neural network. And we're also going to be looking into model parameter opportunity for neural networks. And also finally check out tensor boards, how you can use tensor boards and how it works. The links that can also help every one of us understand TensorFlow and get started. So I also want to make everyone understand that I'll be sharing Medium articles on each of all these things, and I'll be explaining each line of code. So I would advise that you check out the Medium articles that will be following this video. As I'm done with this online session with you guys, I'll be sharing this video. I'll be sharing the Medium article. So I'll advise you check it out, you read, so that you can understand better all the things we're going to be talking about. So what next? So everybody always want to they don't know what next to do, or though some people do. Alright, so you've tried out a lot of basic machine learning algorithms like logistic regression, examples and the likes, and then you want to try something much more robust or something much more bigger on your data. Sorry, so you want to try something much more robust or something much more bigger on your data. So you want to get started you want to try a neural network on your data. So TensorFlow is actually the first library you would want to experiment with in solving your problem. Alright, so TensorFlow prerequisites. So what are the things you need to understand about TensorFlow prerequisite? So for you to be able to code TensorFlow easily, you have to be very convenient with Python programming. You have to have a good grasp of object-oriented programming. You have to get familiar with NumPy operations. You have to know how to handle errors. You have to be able to debug, and that's very, very important because you come across a lot of errors. But what keeps you going is having this understanding. Okay, that once you get this error, okay, this is what it's pointed to. This is what I need to transform. This is what I need to correct. So that's why I'm putting that. It's very, very important. Alright, so let's look at the introduction to TensorFlow. TensorFlow is a symbolic math library, and it's used for machine learning applications such as neural networks and deep learning. It's vastly used for this application. So TensorFlow was developed by Google Brain team, and the first version was released in 2017. And it's an open source library written in Python and C++, CUDA. It's also a cross-platform application that's available on Linux. So if you're a Linux user, you can run TensorFlow. If you're a Mac user, you can run TensorFlow. If you're a Windows user, you can also run TensorFlow. Alright, so TensorFlow was coined from the word tensors. So tensors are basically containers that can house data in n dimensions. Just like you have a matrix. A matrix is just a two-dimensional tensor. So but tensors can help you express things beyond just 2 dimensions. You can actually have thousands, millions of dimensions, depending on the kind of problem you're trying to solve or the kind of problem you're trying to use it for. So let's see how we can set up TensorFlow. So regarding the setting up of TensorFlow, I would say, so you have to get TensorFlow on your PC. You can first of all download Anaconda, and then after installing Anaconda on your PC, then you can now go to your Conda prompts and then create a virtual environment on your Anaconda. If your PC is just, if you want TensorFlow for CPU support, you can just create a virtual environment and then install the version of TensorFlow for CPU support. and then you activate the environment. So um, for those of you that want to use it for the GPU support, you need the GPU support for TensorFlow. You can also do the same thing, create environments, then install the TensorFlow for GPU support, and then you activate. Or better still, for people that might be getting a lot of errors, environmental problems, actually creating virtual environments solves your problem the best. But in case you're gonna be having that kind of a problem, so I'll just advise you just do pip install TensorFlow and then the version. It works for Linux or Windows. Depends on the platform trying to you're trying to address. So you install, pip install, whatever. So let's go into the TensorFlow operations. Alright, so I'll be taking you guys through the fundamentals of TensorFlow. Alright, so I'm running this on Colab. Alright, so I have TensorFlow imported TensorFlow as TF. So the version of TensorFlow on Colab here is 2.2.0. Then you can also do the same thing by importing some other libraries that would assist you in understanding this very well. So I want you guys to pay attention to these two blocks, these two lines here. The reason why is that I'm trying to implement TensorFlow, low-level TensorFlow. So that's the reason why I'm importing TensorFlow this way. And I'm also disabling every form of eager execution that might want to prevent me from, having that low level. You get so. All right. So, for example, so one of the things I want us to look into is, okay, just as we have in pure Python, you have variable declarations. So I have a variable called my age. I have x, y, z, and I want to compute x cubed plus x squared times y, then plus yz. So when I do that in pure Python, it gives me this. Now, if you want to do this in TensorFlow, this is how you do it. So you create a variable by using tf.variable, you specify the variable value, and then you can also give it a name. It's not compulsory, but it's cool if you give it a name. Now, this name that you can see, it's the name ascribed to everything you declare. For example, because it's a variable, it's the name assigned to the variable I'm going to be seeing on my TensorFlow graph. So if I go to my TensorFlow graph right now, if I create this and I open up my TensorFlow graph, I'm going to be seeing a variable called x because I've named it x. But if I don't name it x, it's just going to give it random names. So you are putting these names because you want to be able to track what you're doing. So I have f to be s cubed plus s squared times y plus yz, and I want to print f. If I print f, it's just going to give me this. So now, in order for you to be able to run this, so I can get this, you have to put it in a TensorFlow session. Alright, so, and that's what we have here. So you call with TensorFlow session as SES, you initialize the variables that you want to use. Now this TensorFlow global variables initializer helps you to initialize every variable that is required for your TensorFlow graph to run, or for it to perform computations. So you initialize that, and then you can now evaluate the function or the things you've written in TensorFlow. You can now do your computations. All computations have to run in your TensorFlow session. Alright, so you have that result. Okay, so you can also have constants like this. You can also have constants. Sorry, a minute. Excuse me. Alright, so you can have a constant, you can have, okay, so I have a constant called 3, and I have a constant called 12. So I want to add, you can add constants, you can add values, then save it to a variable, and also you can also run it in your TensorFlow session. Then you have so that's 12 plus 3 minus 8. When I run this and I evaluate, I have 7. Alright, so don't worry, all these things are well explained in the Medium article I'll be sharing after this session. So please do well to read and so you can understand better. So matrices. you can do matrices in TensorFlow. So I have a matrix called M. It's a matrix of ones with 20 rows and 5 columns. Then N is 5 by 20, and K is 5 by 5. So I want to multiply M by N. So which means the rows and columns of the matrix have to be the same thing before you can actually have a multiplication. That's matrix rows. And then the multiplication, the result of the multiplication, I want it to be added to another matrix, which is a 5 by 5 matrix. So when I do that, so I have Y to be the computation of everything I just wanted to do. So tf.mathnew means tf.matrix multiplication. So the first matrix, the second matrix that I want to multiply, and then you wanted to add it. I want to add it to the next matrix. So Y is equals to tf.mathnew this, and then you can now run this in a TensorFlow session, and then you have this. Actually, this is zeros, this is ones, this is zeros. So when you multiply ones by zeros, you actually have zeros. So, and then when you now add zeros plus ones, then you're going to have ones. So you can. So one thing I also want you guys to understand is when you run TensorFlow sessions this way, when you evaluate the attributes, the result is always the result will always be in form of an n-dimensional array. So you just to confirm, see, so printed the matrix and confirms it tells me it's a NumPy array. So you can find matrix determinants. So I have an array. So I have this array of floating point numbers. So I want to find the determinant. So I created a variable v. So I said it should find a determinant. I want v to be the determinant of this matrix. So by the time I run this in TensorFlow session and I evaluate, I have this as my determinant. So you can actually try this out. You can try pen it down, write it, and then you'll see you actually going to have this. Alright, so you can also do inverse of the matrix with TensorFlow. You can perform inverse of the matrix. So the matrix I'm using here is ARR, which is this matrix over here, which is this matrix over here. So by the time I find the inverse of the matrix, I evaluate and print, I have this. So you can do inverse of the matrix in TensorFlow. You can also have diagonal matrix, and this is how you call it. CF just matrix dia. So you pass in what you wanna have the diagonal of. So you pass it in. So I want to have the diagonal of the inverse of the matrix, which I just computed before now. So I have all of this. So what matrix diagonal does is for every matrix you pass in, for every row, it turns each row into a diagonal matrix, and that's what you can see. So you have 0.08, so you have that 0.068, you have this 0.21, you have this. Then the same thing, this, you have this, you have this, and others. Alright, so you can also find the transpose of a matrix transpose. So all you just need is to just call this function matrix transpose, and then you pass in the matrix you want to transpose, and then of course you have to initialize your variables, and then you can now evaluate and then print out to get the result. Then hard marks, I'm just trying to make you guys see things you can do with TensorFlow. For example, I have an array of 4 numbers, 3, 4, 20, 15. So I'm saying that, okay, I'm saying that variable this on my TensorFlow graph, its name is this, and then I want to find the argmax of this array or set or list. So when I have evaluated, it tells me that the argmax actually returns the value, the index, the value that has the highest value, the index of the highest value. So as you can see, 20 is the highest value. Yeah. So what's the index? 0, 1, 2. So that's why we have 2. So that's what argmax does. That it's maximum argument. So admin also does the same thing. Value the entry with the minimum value. All right, so so you can have addition in TensorFlow. So you can add two variables A and B together. Yeah, just like I said above before. So you can add you can use TensorFlow to add two things together, then evaluate it in a TensorFlow session. You can also do argmax according to axis. This actually works best for arrays. So I have an array called ARR, which I've defined, before getting here. So I wanted to find the maximum argument according to the columns. When you set args equals to 1, that means you're trying to refer to columns. So so for example, ARR is let me see. ARR is this field, is this. So we have 2, 4, 6. So what's the maximum argument? What's the maximum according to this? So let me just copy this so we can just compare. TF.session. Okay, so where are we? Oh, alright, I've already printed it here. So when I say argmax, tf.argmax arrays, so look at this now. So it returns 2, 1, 0. So now it's telling me that according to this, the maximum entry here is 6.6. And what is the index? 2. The maximum entry here is 8.2. And what's the index? 1. The maximum entry here is 7.4. And what's the index? 0. So that's what argmax does. So you can also do argmin, and then you have this. Then you can also sort arguments. Argsort. Now the thing is, it's going to sort arguments. It's going to sort the matrix column wise from ascending in ascending order. I want to sort it in ascending order. So in this case, I have just as I have here AR. So I have 2, 4, 6. Now 2, 4, 6 is already in ascending order. That's why we have 0, 1, 2. Now if we go to 6.6, 8.2, 1.1. Now you discover that 1.1 is not in ascending order. So I want to arrange it in ascending order. So what's the index of 1.1? That's 2. That's why we have 2 here. Then 6.6 is 0, 8.8, 8.2, which is the highest is. So you are basically trying to sort, and that's the same thing with the last one here. You have this. So you're basically trying to sort the array based on their lattice column wise in ascending order. Just want it arranged. So you're just going to return the indexes of all those things in ascending order. So you can also do confusion matrix. So in this case here, I just have okay, I want to find the confusion matrix of two arrays. So I have A to be an array of random values, uniform random values between 0 and 1, and I have B to be the same thing, 0 and 1. So this is just for you to guys understand that you can also do confusion matrix. So I sealed everything else. So we are going to be have 0.this, 0.that, dot this, dot that in float. So but when you now do tf.seal, so tf.seal just approximates it to the nearest value. So so confusion matrix predicts and then while true, just like you do in scikit-learn. So I just say, okay, on TensorFlow, I want the name to be confusion matrix. So when I run this in a session and I evaluate the confusion matrix, I have this. So that really means you can actually have confusion matrix of you can actually do confusion matrix in TensorFlow. So you can do casting. You can cast values. That is casting. Basically, you're trying to change data type. For example, I have this to be a constant of an array. So 1.8, 2.2, 3.5, 4.9. So I have them to be a float. So I just want to cast everything. I want everything to be integers. So when I do that, I have all of this. You can also do cumulative. You can do cumulative of everything. So by that I pass in cumulative because it's just an axis. So I just said axis equals 0. So that will be 8.8 plus 2.2. Start from 1.8. Sorry, 1.8. 1.8 plus 2.2, that's 4. Then 4 plus 3.5, that's 7.5. And 7.5 plus 4.9, that's 12.4. Now placeholders. So we have placeholders are basically like inputs, and you guys will be seeing the reason why placeholders are this. So placeholders are why we'll be using placeholders. So placeholders they are more or less like they are like dummy inputs, like inputs to dummy containers. They hold information to be processed. So it's more or less like you have a pipeline a pipeline whereby a data pipeline, such that once you pass in this, you want the pipeline to operate on that and then give you a particular result that you desire. You want the data to pass in through those pipelines. So placeholder is just, you can actually say placeholder just like that. Do you understand? But what makes it different from all other things like variables and constant is that you can keep adding value. Oh, let me check my internet. My internet is yeah, so internet. Alright, so my internet is up now. Alright, so for example, now look at this placeholders. I have a placeholder. A as a placeholder. So the inputs are always floats, and I want it to take anything as long as it has 3 columns. Just taking anything as long as it has 3 columns. So for example, look at this now. I want B to be A plus 5, that is element wise. I want B to be A plus 5 element wise. So defining this in extension in a session now, in order to be able to evaluate B requires a data for it to operate on. So that's why in placeholders you have this feed dicts of a thing. So feed dict is more or less like it takes in every information that is needed for what you want to evaluate. So for example, for B to be evaluated, I need a data of at least 3 columns, and B would do what? Just add 5 to each entry element wise. So by the time you look at this now, I have an array of 3 columns, just 1, 2, 3. So by the time I do that, so you have 6, 7, 8. That's B val. So B value also, by the time I do that, this is just a 2D. Do that, it adds every entry element wise. So placeholder helps you. It helps you to keep adding those values. All right, so let's get back to masterclass. So now I think we all understand the basics of TensorFlow. Now let's look at let's look into neural networks with TensorFlow, losses, optimizers, activation functions, and neurons. All right, so I have this here so that you guys can actually understand how a neural network works. So this is an input data that was flattened. This is just a digit that is actually 28 by 28. Some of them come in form of 28 by 28 or 32 by 32. So it was flattened into 784 input nodes. So you pass this into a neural net. This is what we want our neural network to learn. We want it to recognize digits, to understand digits, and then tell us, oh, this digit is 0 or 1 or 2 or 3 or 4 or 5, 6 or 7 or 8 or 9. So in this case, as you can see, it gets in, it keeps computing, and then it's, okay, look, then it computes here, and then it says, oh, this thing is 2. So basically, we're trying to make the neural network understand the mapping between input and what we actually want it to know. So now, one other thing I want you guys to understand from this is, for a neural network, you have neurons. So these are neuron cells. These are neuron cells. Now, a neural network is in this format. You have the input, then you have the hidden layers, and then the output. So now the input must always have the pattern of what you want it to learn. So the hidden layers are actually the guys involved in learning everything regarding the input, and then the hidden layers then say, okay, as a result of my learning of this and learning of that, oh, this is this. So this is our desired output. So for a neural network, you specify your desired output, you specify your inputs, then you specify your inputs, your hidden layers. So your hidden layers can be you can specify hundreds of thousands of hidden layers. It depends on, but the thing is, most times we will look at how we can actually optimize and then make our decision on the number of neurons that you have to select. But moreover, I would love you all check out the write-up by Rising Odegwa on neural networks from scratch in NumPy. He explained all of this in details. So one thing I also want you guys to understand is, these are layers, and then these are neurons, and then what connects a neuron to the next neuron is what we call synapses. And then alright, so for example, this neuron is connected to all of these neurons. This neuron is also connected to all of these neurons. So we have that, they have the same thing for all neurons. So every neuron is connected to the next neuron, but not connected to its counterparts. Every neuron in a layer is connected to all neurons in the next layer. That is, this neuron is making contribution to all neurons here. This neuron is making contribution to all the neurons here. This neuron is making contribution to all the neurons here. So that is the way it learns, via synapses. Alright, so one thing we also need to understand is what we call activation functions. Activation functions are computational functions for neuron cells. So all those neurons are actually cells. So what activation functions basically do is, they are actually algorithms that enhance learning in each neuron. So an activation, for example, you have a neuron cell, it's trying to, just as we have here, look at this now. We passed in an input 2. Now, some of the things around these 2 are dark. So just as you can see, few of these nodes are inactive. It's not like they are not receiving input, they are. But one thing you need to understand is, when you pass in an input, all the nodes that needs to be activated with respect to a particular input gets activated. So with respect to 2 now, these are all the nodes that you see in green. All the nodes that you see in green, they are the nodes that get activated in recognizing 2. Do you understand? And it's not all nodes that gets activated for each input. So for everything you're trying to learn, every node gets the neurons that concerns that input gets activated. So what helps in activating all of these neurons is is the activation function. So the activation function is actually the one helping all these neurons to understand and to comprehend the input and then say, oh, this input is 2, this input is 1, this is 5, this is 3, this is 4. Do we all get that? So that's actually the way it is. So examples of activation functions are ReLU, softmax, sigmoids, ILU, etc. So we can have, so for example, this is the sigmoid activation function, and what it does is, once the summation of every previous, okay, for example, this is sigmoid. If we are using sigmoid is mostly used for output layers, and it's mostly used for binary classification, as you can see. So sigmoid, the way it works is, whatever the inputs may be, you can only have 0 or 1. Now, if the input to the neuron is less than 0, sigmoid would allow that neuron, would set the neuron value to 0. But if the input value, that is the summation of all the computation, all the values from the previous neurons, once it gets to that particular neuron and it's greater than 0, or it's getting bigger, then it's most likely that value would be 1. So that is the way sigmoid works. Either it's 0 or 1. So ReLU is whatever the value, if the value is less than 0, I remain 0 as output. But if the value is greater than 0, then the value would always be the value it has been able to compute. So if the sum of all the neurons in previous layer is 0.05 something, so ReLU we output 0.05. That's just max. So the maximum between 0 and 0.05 is 0.05. So ReLU will output 0.05. That's why it's kind of it's a linear function. But anything less than 0, it would approximate to 0. So for example, if you have -1, what's the highest maximum value between 0 and -1? So it's going to set the output to 0. So that is ReLU. So every of these activation functions, they have their use, their application, but one thing I want you guys to understand is ReLU, it has been proven that ReLU works best for hidden layers. It works best for hidden layers. Then TAN also works for some applications of problems for hidden layers. Sigmoid is mostly used for output layers, though you can also use it for some hidden layers and some of the like. So we also have other forms of activation functions. So let's look at losses. Now, what are losses? So for example, after, just as you can see, there's an input, it feeds, and then everything gets here. Now the thing is, how does it know whether it has actually predicted 2 correctly? So that's what we call losses. So losses basically helps to compute. It basically helps to compute what the network has learned with respect to what it's expected to learn. So if what we expect it to learn is 2 and is telling us 1, then it means that the variation is still much. So it still needs to learn. It needs to keep learning, and that's what led to what we call backpropagation. So after learning, it computes its own errors. Of course, it computes its own errors, and then the error now backpropagates to all other layers. It updates the weights and biases of all other layers so that it can recompute and then repredict again. So it keeps moving forward, moving backward, moving forward, moving backward until the loss is approximately 0, such that it's able to predict 2 accurately. So that is what we have as losses. So we have different type of losses, and they have various applications. So we have the binary cross entropy loss, we have the categorical cross entropy. This is the maths. I might not be able to go into too much math of all these things, but I would love you guys to check out my medium article on this, so you can understand this thing comprehensively. So we have the cosine similarity, we have the mean absolute error. So these losses, they help to enhance learning in our neural network. So if our neural network doesn't compute those losses, then it's not learning. But these losses helps to do that. Now, so we also have mean absolute percentage error, we have mean squared error, and a lot more. Alright, so another thing I also want to talk about is optimizers. So what are optimizers? Optimizers are also algorithms. All these things are algorithms. Neural networks is basically algorithm. Do you understand me? So we have optimizers like ADA Delta, ADAM, RMS Prop, ADA Max, ADA Grad, NADEM, SGD, stochastic gradient descent. So for example, look at this. This is an optimizer. This is ADAM optimizer. Now the thing is, what are optimizers? Optimizers are basically algorithms that helps to maximize learning in our neural network. So we don't want the neural network to keep learning and then keep learning. Definitely there's going to be a point at which it converges, whereby the learning is optimal or the learning is saturated. So all these optimizers helps us to, they are algorithms that helps us to, that helps the neural network to effectively converge and learn. So if you look at this is delta theta. So this actually, I might not be able to go deep into this, but just this j theta is the cost function. This delta theta is actually a differential representation of of with respect to every parameter that's been learned. B1, B2, M, S, B2, S, and everything. They are all parameters that we want to optimize. We want to keep, they are parameters that we supply to this optimizer in order for it to optimize our algorithm so that it can learn. So when your optimizer is at work in a neural net, all these values, they keep learning, they keep optimizing, they get updated regularly. So for example, M gets updated by dividing it, whatever the value might be, with respect to 1 minus beta, the transpose of beta. So beta 1 is more or less like, it's a matrix. So you have that. So you also have the same thing for S, and then theta. Then one other thing I also want to talk about is N. So now N is the learning rate, the rate at which the optimizer is making the learning possible. So if the learning rate is very, very huge, if it's very, very big, it's most likely not going to converge. It might converge, but it's most likely not going to converge, or it might converge and not reach the optimal convergence point. You get it? But if the learning rate is very, very small, do you get it? It's likely going to converge, but might converge at a slower rate. So these are things we need to understand that they actually work. So all these optimizers, they all have their own application. They all have their own use cases. So we have the same thing for RMS prop, AdaGrad. This is the gradient descent algorithm. Got it. The weights being updated, the biases of every neuron being updated with respect to the learning rate. This value is the learning rate. So let's put all of these things together on a data. So let's look at our Titanic data set. But before we get to Titanic, I would love us to look into the house pricing data. Alright, so house pricing, yeah. Alright, so that's it. Mistake from the keyboard. Alright, so import the necessary libraries. Of course, you have to do this because we actually want to do this in low level, so you have to do this. So the data set, I'm just trying to use it from scikit-learn. It's available on scikit-learn, so I just imported this from scikit-learn, and then I have this. So this is the data. I won't believe everyone watching this has a fundamental understanding of pandas, numpy. So I won't be going into the deep of all of this. So we all know what all of this is. So we have inputs. We have how many? We have 18. We have 8 columns. We have 20,640 entries that we want to operate on, and then we have a target. So this is a regression problem. So let's see how we can use TensorFlow on this. So I have my sklearn to split in the data. So my test size is just 20% of the data for test, and then the rest for training. All right, so let's just see. Okay, assemble. Okay, when I pass this through a gradient boost regressor without tuning, so without tuning, and I made mean squared error as my loss function, more or less like that. When you say loss, that is, we are talking about the evaluation metric. You get it? So but when I check the accuracy of the training, it's around 80.48%, without tweaking the parameters. But when I checked the error was 0.2940. That is very, very, very good. That shows that this algorithm is doing very, very well. The error the error difference between its actual value to the predicted value is very, very small. That means it's predicting the values almost accurately. Do you get it? So our desire is to have this to be approximately 0. But once this is getting to like let's say 2900 thousands, it means that it hasn't learned enough. Now what I want us to see is, okay, let us put all of these things together and see if, let's see how our neural network would operate on this data. Let's see the performance of our neural network on this data. All right, so now one thing I want you guys to understand is not all data requires a neural network, and most data we work with, they all require neural network. So it's very, very important you understand. That's why it's very important you understand the mathematics behind you understand your data, number one. Then you understand the mathematics behind the algorithms that you're using, so that you won't just be using them blindly. So that, for example, if you know that this is just a simple classification and there's no much complexity. Okay, let's say you have a classification problem and there's not much complexity in that data. The best algorithm you want to use is a logistic regression algorithm. Okay, you might want to try that out first before you now say, okay, let us try out assembles. Do you get it? Now, if the data is not complex, there's no need for you using neural networks. Do you get it? So this is just for us to see how this thing works on data, how you can apply it on data. So you can always have your data in this just the same way I've been able to. I'm going to be working on the house pricing just the same way. So all right, so let's just, okay, so I wrote a simple function here that is going to help me compute my accuracy, because I kind of like writing things this way. Well, actually, I think TensorFlow also gives you the support of helping you determine your accuracy. So we're actually going to say that. Okay, let's try and manually compute the mean squared error with the use of optimizers. All right, so I'm trying to import. I'm trying to clear all sessions. I'm going to talk more about this later, but I will talk about this later. All right, so I have my batch size, because I have over 20,000 information here. 20,000 information that I want to process here. So okay, I just said, okay, let me set my batch size to 1,000, and then let me say, okay, what's going to be my number of batches? So my number of batches here should be, okay, yes, okay, so I'm saying, because my X train my hex train here. My hex train is 16,512. So since I'm going to be feeding that into my model for it to learn, so how many times will I have to feed that into my model to learn? So that's the essence of the batch. That's the essence of the batch size. Where is it? Yeah. So I have 17 of it. So you're going to have the first 1,000, this 10th 1,000, the 16th 1,000, and the last of it to just be the 17th iteration is just going to be containing 512 informations to be processed or to be learned from. Alright, so I also wrote a little function here that would help me feeding my data in batches. Alright, so I wanted to do it such that, okay, once I say give me batch, because it's going to be fetching me my data has 17 batches. So if I say give me, I don't want to be feeding batch 1, batch 2 recurrently. I don't want to feed batch 1 10 times or batch 2 10 times. So I don't want to be giving my algorithm the same data to learn from. So I want to be feeding, okay, feed batch 0, that's a data, then feed another batch 1, feed another batch 2, feed another batch until I get to the 17th batch. So as I'm feeding those batches, the algorithm is processing the data, it's learning, then the next batch it comes across is a new data, and then it learns from it, it moves to the next data until it completes all the batches. By so doing, your algorithm gets to learn. You don't want to be feeding the same data to your algorithm. That's not an optimal way of learning. So what I did is, okay, if my batch index, that is what I'm passing, is less than n batches, I have 17. So 17 minus 1, that's 16. So since I will be starting with 0, I'm going to be starting from 0 to 16. That's 17 batches. So by the time I say, okay, give me batch 0, so it's going to check 0 less than 16. That's 0 is less than 16. That's true. So I'll tell it, okay, start from the start is just going to be batch index times the batch size. So that will be 0. So it's going to be starting from index 0, and it's going to be stopping from where it's going to be stopping from batch. It's going to be stopping at batch size plus where it started from. So it's going to be taking just 1,000 of it, and then it's going to be setting into X batch, Y batch, and then returns that to me. Now, if it is not, now, if the batch index is greater than, so for example, by the time it gets to 16, right? Starting from 0, it gets to 16. So it's checking 16 less than n batches. So 16 less than n batches minus 1, that is 17 minus 1. 16 is not less than 16. So that means we have actually gotten to the last batch. So what I just wanted to do is just because I don't want it to just be looking for 1,000 batches, whereas the last batch just contains 512 data points. So I just wanted to fetch the last batch from it. So that's why we have this else sign. So that's what this fetch batch does. So my train, the X train, Y train, this the shape of it. So I have M and then N. So now let's define our placeholder. Now you guys will get to understand more why we are using a placeholder. In this case, you won't want to use variables or constants. The reason being that you don't want you want to be feeding information. So that's the reason why you will be using a placeholder. But if you're using a variable or a constant, you don't want to be overwriting the variable, or you don't want to be overwriting the constant. You just want them to be what they are. So placeholders gives you the flexibility of feeding in information and then performing the operations you want the algorithm to perform. So my placeholder, I wanted to always take in any amount of information, but they must have 8 columns. And then the same thing for my Y, any amount of information, but it must just have just 1 column. So on my TensorFlow graph, my input is X. Then on my TensorFlow graph, for my Y it is Y. Alright, so the first thing we want to do is, okay, let us first of all have the loss. Let us do the let us have, we are trying to, what we are trying to do is we are trying to compute the mean squared error with the use of optimizers, right? So let's compute the loss. So in this case, our loss is just going to be mean squared error. Now, if you look at, let me go back here. If you look at this, mean squared error is y true, y predict, that is the actual value minus what you have predicted, square it, then divide it by the number of samples, number of predictions, which is n. Do you get it? You have to sum every iterations that you've in that entry. So look at, let's get back to it. Our same price. All right, so and that's what we have here. So we said, okay, first thing we need to first of all define weights and biases. So in TensorFlow, weights and biases, I define it as a variable. So my weights, I want it to be a random weight of this, then standard deviation. I want it to select, to determine the weights based on standard deviation and name it weights on my TensorFlow graph. The same thing for my bias. Now the reason why I have 8 here is because I have 8 columns being operated on. That's why for my by the time you do that, if you have that, so you have random normal. And for your bias, I want my bias to just be a variable of zeros. Then my prediction, my y predict will not be, my just simple linear regression algorithm. This is a regression problem, so let's just have a simple linear regression algorithm. So in this case, we have x, which is what we want it to learn, and then we have w, which is more or less like the gradients, but in this case it's actually the weights, and then b is actually the biases, but in linear regression, it's more or less like the intercept on the y-axis. So it keeps learning things using this pattern. So after multiplying the input x times w, you had whatever you multiply plus b. So you should have a single value. After doing all of that, you should have a single value for every entry. So you have y predict. So what's going to be the error? The error is going to be your prediction minus the actual value. That's the error. And then mean squared error does what? It's just going to square it and then find the mean of all the squares. This y predict minus y, they are actually arrays of everything you've predicted. So it's going to take them elements wise and then square each corresponding element. So it picks this from y predict, picks the corresponding value in the actual in y, and then it takes those values, find the difference, which is the error, squares them, which is what we have here, and then it does that for all the entries, all the things you've predicted with respect to the actual value, and then it finds the mean. So the mean is actually the MSE, the mean squared error. So now we have our loss in place. Now the reason why we are, like I said, all these things have to run, they have to run this way, more or less like you're trying to define them. Now the reason why I have tf.namescope is, okay, for on my TensorFlow graph, I don't just want all these things scattered. I don't want to find it difficult looking for, okay, where is my loss taking place, or where is my training taking place, or where is the optimizer. You get it? So tf.namescope basically creates more or less like a graph container for all of these operations to take place. So by the time I go to my TensorFlow graph, which I'm still going to show the tensor board, I would see something called loss. So from there I'll be able to see how the loss is interacting with every other information in the graph. So don't worry, we are still going to see all of that. So the same thing, training. Now after completing the loss, right, I want to train. Don't forget, we've not built a neural network. This is not a neural network yet. We are just basically trying to see linear regression in action here, but using TensorFlow. Do you get it? So now when I want to train, I want to use an optimizer that would help optimize my training and help make this learning converge. So I want to use, I'm importing learning rate to be equal to 0.01 because I want it to converge. That value is more or less like a generic value it's more or less like a value that always reaches convergence point, optimal convergence point. But you can actually set it to 0.01, you can make it smaller. But the thing is, the more you make it smaller, the more time your model has to run before it converges. Because your model will not stop until it converges to that. So it's going to take more time. So, but just to start with, let us have learning rate to be equal to 0.01. So my optimizer here is RMS Pro, and I'm setting its learning rate, the rate at which it's learning, to be 0.01. So now one thing you need to do is your optimizer has to be working on a metric. So in this case, our metric is MSE. So we want the optimizer to optimize the mean squared error. So that's what we have here. So you just like I said, you have to initialize the global variables. Okay, train saver. So if you want to save the model or the training parameters of your model, you can have this. All right, so you have train loss, test loss. Don't forget, we are getting at something. So now, in order to run everything that you've initialized out there, you now need to create a TensorFlow session. Now, the rate at which I want my network to run, I want to see the computation of the progress of my network. I want to just have 10 epochs. That is the rate at which I want to see my algorithm displaying the results to me. I want 10 results from the information being displayed to me, just for me to know how it's learning. All right, so everything has to run in session, TensorFlow session. So init.run, just like we've already initialized it here, so it's valid. So by the time init.run, it's every variable needed for this program to run gets initialized. Now, for every epoch, I want to see some computations. So I have my batch step, average loss, total loss, just initialized. The total batch is xtrain dot shape 0 batch size. That's the total batch, which is 16,512 functions that I want to process. So now one thing I want to do is, okay, I want it to keep learning in batches. I want to feed this thing to my algorithm in batches. So that's why we have this fetch batch. So when this fetch batch, I believe we remember this. It was defined from the beginning of the program. So we have the fetch batch. So once I say, okay, for batch index in range n batches, so we have 16 batches. So we have 17 batches. So we're going to start from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it's not going to reach 17. So because 17 is not part of the batches, so it's 17 batches, but it's starting from 0 to 16. So by now I say x batch, y batch. So I pass fetch batch 0. So it takes in the first batch, it gives me what those first batch is in my data from my X string, and then I take this, pass it to my session. So now what I want to run is my training hub and MSC. And now in order for these guys to run, these guys have been defined already. Yeah. So they've been defined already here. So in order to have them run, I need data to be fed into them so that they can give me results. Do we get it? So that's why we have this feed dict. So this X corresponds to, it means we are referring to this guy, and then this Y means we are referring, and then Y also, right? So that's why. So if I change this to a small letter and I run, it's going to tell me it doesn't know what small letter X is, because small letter X was not defined from the start. So the same thing Y. So for every batch, I want to keep running I want it to train and then reduce the loss, train, reduce the loss, train, reduce the loss until I have all the data totally fed. Then I want to monitor my batch steps and the total loss. So after running after running all the batches, definitely the algorithm has learned, because error keeps getting reduced, this keeps getting reduced, and our optimizer keeps making our model optimal. So I want to be able to print out my my epoch training. So I want to see the evaluation of my model. So what I do is I just define this epoch, print out the epoch, and then it tells me what is the loss. What is the loss? That is the average loss, which was here. So average loss. And then how did I, okay, so how I computed the, average loss here. So the means, the MSC, now after it has learned everything for the first epoch, it has learned from all the data in batches. Now I'm now evaluating the model. I want to know the minimum error the model can now evaluate to. So I need to feed it with X train, Y train, which is the data that contains actually all the things that's learned from. So what's the minimum error the model has been to learn from? So that is the training. That should be training error. That should be training error. This should be training error. Then the test accuracy, that should also be test error. So I also feel that this is what it hasn't learned. It hasn't seen this data before. X test, Y test. It hasn't seen this data before. So I want to see it evaluate this guy, make its prediction, and then tell me what is your minimum error. So that is what. So in order to now keep track of the training loss and the test loss for every training, for every epoch that I run, so I just keep appending the error being computed to an array called train loss and then test loss. That's for me to just visualize or to see, so I can plot them and see how it's learning. So I can, and the same thing. So the reason why I have this if else is I just want it to just run this false. I want it to only run this if program when it's starting and when it is ending. So I don't want to see too much of all these things printed here. So I just want to see the start value and the end value. So and finally I print my error, validation, training, validation error, training MSC and validation error. So and you can also save your session. So this will be CKPT. So CKPT. So by the time I did my training, the first epoch, it told me the average training loss was 143.44. Training accuracy, that was training. Let me run this from the beginning. Run time. Run. Alright, so while we wait for collab, I think my data is, let me open it. Okay, my data is on. Let's see. Okay, just started. Still connecting. Still initializing. Cool. Alright, so as you can see, alright, so we have all of this. Now, by the time now look at this now. So it tells me average training loss, training error, test validation error. For the first epoch is this. Do you get it? So this is my GPU, is the runtime notes. Okay, we don't need a GPU to run this. It's simple. So it tells me model complete. The final training MSC is this. Final validation MSC is that. That's actually very, very poor compared to, it's not that as optimal as we expected compared to what we have here from, which was 0.29. So what does that tell us? Not all model requires deep learning or neural networks. So in this case, we can basically say deep learning the neural network here isn't performing as more as we want it to do compared to that of the ensemble which we used earlier on. So, but actually, for us to actually know that this thing was actually learning, look at it started. When it started, the error was very, very huge, 182,308, and then the test validation error was very huge. That is, it doesn't know what it was predicting. It wasn't learning. It wasn't getting it very well. The error in its learning was very huge. But if you look at it, at the end of the training, all this error reduced to this. That really showed that it actually learned a lot. But one thing you can also discover about this is I can actually increase the number of epochs here and then see if it will still converge to, okay, let's see it's there's no bad thing if we, okay, let's say if you set epochs to, you can actually let's set epochs to 20 and see. Let's set epochs to 20 and see. Alright, so it tells me at the first epoch that was the value. Alright, believe you're getting it. So I would advise we all check the Medium article. I have a Medium article on all of this, so I'll be releasing them out for all of us for everyone to see and understand. So by the time we increase number of epochs, let's wait and see what happens. So this is at the first epoch, 11th epoch. So let's see what happens. Let's see. This is the loss, but look at the error reduced from 125 to 58. So actually, if we can keep increasing the epoch, if we increase the epoch to like maybe 50, definitely we should be drawing close to zero. But another thing is models could overfit and things like that. But let's just be silent about that. We'll get there. So when I visualize my training for 10 epochs, see this to show that yes, the error was reducing. It's actually learning. And then when it got to 2, it was more or less like it seems as if it has reached its convergence point. But when we actually see it here, it says it reduced from 120 something to, see, from 125 to 58. That was half. You get it? This is what, so we can actually visualize that also. So this is to show that it's actually learning. The epochs. So now let's build a neural network. Now, how do we build a neural network? Now, when I'm talking about building a neural network, I want us to build a neural network that has hidden layers. So number of inputs is 8, hidden layers is 40, hidden layer 2 is 100, hidden layer 3 is 20, and then the output is 1. So now, just like we did the first time, now look at how to clear all sessions from the first, so that if I visualize my tensor, because the reason why we have this is if I go to my tensor graph right now, it's going to be showing me all the sessions. It's going to be showing all nodes and everything that I've run related to TensorFlow. So when you clear the session, it only shows you the session of what you're actually trying to train. So now I created a function called neuron layer. So this neuron layer basically helps me to create my neurons. So what I want to do is I want to have 8 inputs at my first layer, and I want to have one single output. Do you get it? Because it's a regression problem, just one single output. Then I want my first hidden layer to be having 40 neurons, my second hidden layer to be having 100 neurons, and my third hidden layer to just be having 20. This is just to experiment. You can make the numbers big. And the reason why I'm just using these small values is, another thing that determines the number of neurons for your layers is actually the complexity of the data. So I've been able to check, and it's quite like the data is not actually complex. More so, the data has enough information. So it has enough information at least to experiment with. So my neurons layers, so here, just as I created, initialized. So what I did here is, create a name scope just to show that yes, a neuron is being created. So my number of inputs, of course, I want it to be 8. So I'm just using standard deviation here because for the number, for the for the initialization of weights and biases of every neuron I create, every neuron layer I create, I want to initialize, I want to give them default neurons and biases. So with this, I have, so for a neuron now, I want the neuron to be the n inputs and then the number of neurons there. So I'm going to be creating biases, I'm going to be creating weights for n inputs by n neurons. So for every neuron, it has its own weights. So set it to a variable called weights for this particular layer. So for this particular layer, we have weights that contains weights of all the neurons in that layer. Then we have the biases of, so I just want the biases to just be variables of zeros. I can actually set it to the same init here, but I just want it to be variables of zeros to start with. So just like I have, z is tf.max mu x w b. So in this case, the computation, I want the interaction between the neuron, the first neuron, right, and the corresponding neuron and its corresponding weights and its corresponding value to be computed this way, just like a linear regression. And then the activation I want for my neuron cell for this particular neuron, now I will set it. So if my activation function is ReLU, then I want you to do ReLU operation on that prediction that those neurons are given. So we have that. Else we have return z. You just want the discrete values. So we create the neural nets using with tf.namescore neural nets, and then we have the hidden layers connected this way. So I call this function neuron layer, then we have x, which is the input, and then the next layer, which is the first hidden layer, and then the activation function, which is ReLU for that layer. So I'm trying to create an interaction between the first input, which is my input data, and the neurons in the hidden layer. And then the same thing goes for hidden 2. Now I'm trying to create another hidden layer here, such that but I want you guys to understand that as I call this function, all these things are being initialized and done recurrently, like it's done as you're doing this. So the output of hidden 1, which is x and h1, the output of hidden 1, I want it connected to hidden 2. Now hidden 2 is another layer of how many neurons? 100 neurons. So I want them connected. So I'm creating connection of synapses, neurons to neurons, layers to layers by doing that. And then as I'm creating that, I'm also creating the computation. I'm creating how they will be interacting, how they will be computing values for, how they'll be interacting by computing the values of whatever the previous layer is trying to give the next. So for the input layer, it computes values, give it to the next also gives to the next, depending on the number of layers you want to have. So because I just have H1, H2, and just have 3 layers, so I have those 3 layers here that I want to work with. So I'm just going to be having 3 of these things cascaded this way. So for all of those 3 hidden layers, I want the activation function to be ReLU. And now for the heartbeat layer, don't forget, once you have set activation function to be ReLU, then whatever operation that is being done, the activation, the ReLU operation will always take place on every operation being done. So yeah, like I said initially, ReLU is kind of optimized for hidden layers. So we also have the last layer, which is the output layer, which is this. So the number of neurons, I want it connected to the output. So this output, I'm not setting an activation function because I just want it to be the discrete value. I don't want anything. I don't want my output prediction to be tampered with respect to the input. So that's that. So my loss, like now, I just want to implement the mean squared error, just as we did initially. That one was just pure linear regression, but now this is neural network of it. So just as we did initially, train optimizers. I'm also using RMS prom optimizers. Then I run the same training, and then look at it. Boom! Just in 10 epochs, just with a neural net. That one was just pure linear regression, the first one we did the other time. But with neural net in just 10 epochs, I was able to reach 3.0. Started from 132.98.49, and then it's reached this, converged to this. So we can actually also increase the number of epochs, and then we're also going to get close to 0, just like the assemble, which adds 0.29. So now, okay, I'll come back to TensorBots later on. I'll come back to TensorBots. Let me see. Oh, I have not run my. Let me run this. Let me clear out sessions before run this. This. Ah, that's huge. Let's move on. Alright, so look at it now. With your tensor board, I can visualize my scalars. I can visualize the scalars. Now look at this. It's telling me that it started from 2.2 times 10 to the power 4, and then it's converged to 0. So that really shows that it was learning. So this is the train. Why is this thing not coming on? Okay, let me just put it this way. Alright, so this is the train. The blue represents the training, just as you can see the train, and then it keeps track of all of this. This is TensorBoard, and this is the validation, and then others like that. So the mean squared error, because we actually want to track our so we can see all of this. So it keeps learning this way. All right, so you can also see the graph. Okay, let's check the graph. All right, now look at this. I have this name scope defined when I started this session. So we have training defined is a name scope. So if I didn't define this, everything would you just see everything that is inside this guy, which we've already defined there. Then the losses, then the neural net. So for the neural net to work, it needs X inputs, right? And then it enters into the loss. The loss does the computation that is validates between what the neural network is and with respect to the Y. So this loss computes what this neural network is given with respect to the Y, and then it keeps reducing the error. Then this guy trains, it trains, and then it's, if you look at this, this is a feedback. So it goes this way, it comes back, goes and comes back. Please say, so it goes and comes back. So it trains, it updates the neural nets. We have loss again, trains, updates the neural nets, trains, error, trains, updates the neural nets. So I believe we all understand that. So those are the fundamental things you need to, you can, more things you can actually do with your tensor board. You can actually visualize images, you can visualize audio, debuggers, distribution, histogram, text, PR curves, profile, beholders, H param, mesh, what if to, but because we don't have all of that in what we just created, so the best you can just see is just the root mean squared error and our TensorFlow graph. So this is a TensorFlow graph. Yeah. Alright, so now let's move on to Titanic, and let's move on to Titanic. Let's reconnect. Come on. Alright. I have this all running already. So I have this processed already. Let's not spend too much time. We can all do all of this by ourselves. So let's just go to the neural network aspect. Alright, neural network, TensorFlow. So come on. So I have my hex. Now the thing is, now this is a classification problem, and I want to be able to predict the probability that I want to be able to take in various inputs, build a neural network that's able to predict whether somebody's going to survive or not. Now in this case, this is what we're going to be predicting is actually 0 or 1. Now, what's the probability that yes, this thing is 0? Sorry, excuse me. What's the probability that this thing is 0? And then what's the probability that this thing is 1? So let's move on. Let's see what I did. All right, so I just have a simple function here that helps me to just I would explain why I wrote this. The reason being that, okay, let me just explain it. The reason being that I want to be able to build a neural network that has just 2 outputs. Now, the first output is going to be the probability that yes, what you just predicted is 0. And while the second output is going to be the probability that what you just predicted is 1. Do you get it? Now, if for the sum of the 2 probabilities will always equal to 1. So, for example, if after passing in a set of data points and then the probability for 0 is, let's say, 0.7, then definitely that of 1 will be 0.3. Now, since 0.7 is greater than that of 0.3, so which means that what you just passed in, that person is most likely not going to survive, because 0 means not survived and 1 means the person is going to survive. Do you get it? So that's the kind of neural network we want to build right now. So like I said, you import your TensorFlow, you define your placeholders, you have the fetch batch, the same thing, fetch batch. Then in this case, I just to try, I want my hidden layers to be this, my hidden layers to be this, and my number of outputs to be 2. So the number of columns I have in my data processed already was just 9. So just want to see if neural network is going to make a lot of sense of this data. So just as I define my neurons connection, this is low level, so we are trying to make this thing as explanatory as possible. So I define my network, how the neurons will be connecting the neural net. So since I just have 2 layers, right, 2 hidden layers, 100 and 300, so I have my neural nets connected this way, name scope neural nets, and then the loss. Now in this case, I want to be able to use the softmax cross entropy with logits. It's actually a type of loss. Yeah. In this case, yeah, it's going to be predicting probabilities. So it's going to be predicting probability that whether this thing is a 0 or a 1. So the reason why we are not using mean squared error is because this is not a regression problem, and we are not trying to find the error between this and that. So the best metric for me to use here right now is just to use the softmax cross entropy with logits. I'm not just saying you can actually try some others. You can actually try Adam, you can actually try RMS prop, you can actually try some other form of optimizers and losses. But in this case, because I'm using a classification problem, I'm solving a classification problem, I'm trying to use this. So, but in order for you to understand what type of losses and what type of optimizers how to make your decisions on the use of optimizers and losses, I would love you check out the Medium article I'll be releasing immediately after this session. I'll be sharing it with you all alongside the slide. So in this case, I'm trying to use the graded descent optimizer optimizer. So in this case, in the classification, in the regression, we used RMS Pro. Yeah. So for this case, let's just try and see the gradient descent optimizer. I just want to use gradient descent optimizer, and then. Alright, so after defining the neural net and the losses, okay, I want to define the evaluation metric. Now, I want to be able to evaluate. Now, how do I evaluate my model? Okay, after training, I want to be able to see my precision, accuracy. So I actually had to do this at coding. You can actually just do a confusion matrix. Do you get it? You can actually just do a confusion matrix to do this, but in order for you to be able to achieve for you to be able to figure out precision, F1 score, recall, what they call it, accuracy and others. That's how to add code this so that you can all see it. So how do I find my true positive? How do I find my true negative using TensorFlow? How do I find my false positive? How do I find my false negative? And you can determine your accuracy. This is the formula for accuracy based on all this: precision, recall, F1. So with this now, if I can evaluate my model on any of this. Do you get it? So you can always do all of this. So I initialized the variables, and I also saved I'm also declaring this so that I can save my model. Alright, so one-hot encoding is still basically the same thing as that one categorical blah 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 I did the other time. So just as I did the training of my regression problem, so I keep feeding this thing in batches. And I was able to, after running this epoch, the first epoch was, the training accuracy was 63, the test was 64, and after this 11th epoch it became 71, then 74. I just said let us stop there. This was just, I think, this 20 epochs. So if you want to keep learning, you can actually increase the number of epochs to whatever desired value you want to have. You'll get it. So stopping at 20 epochs, this is the training accuracy. So you can have 50, 40, 60, whatever number of epochs that you want to have. So look at this. I just had to just do this so that you guys can see that yes, it's learning. So see, at the first epoch 0, this is the training accuracy, 78. 76. At 1 it was 78, 1.6. Test accuracy was 0.7. It keeps increasing and up to 0.8. So you can increase the number of epochs, and then you're going to have very pretty good performance. Now let's look at how to implement TensorFlow in Keras. We've done new level now. Now, one thing I'm basically trying to introduce Keras here in the sense that Keras was written from TensorFlow. So Keras actually helps us to solve all those abstractions of all those codes, writing a lot of that before you actually do your training. But in Keras, you can actually do all of these things in 5, 6, 4 lines. So look at this now. But now TensorFlow has Keras. You have TensorFlow in Keras, so such that you can easily run TensorFlow without having. You can easily run Keras in TensorFlow without having issues. So you say from TensorFlow to Keras import layers. You can actually just write this plainly in Keras. Let's just see how we can do this in TensorFlow. So the same way, I have my hidden layers to be 100, 300, and number of inputs is 9, number of outputs is 2. So So in this case, I was supposed to specify, yes, this was supposed to be 100, 300. Then this is 2, then 9, you get it. But I'll tell you the reason why I later changed this to this. Later, I'll show you later. So after running all of that, we also have the Keras model. Or better still, let's just run it. So we have 100, we have 400. All right, so okay, let me come on. I'm human also. Okay, think yeah. So runtime. Let's run all. All right, so I'll wait for that. Let's keep at it. So you can also implement TensorFlow in Keras this way. It's very, very easy. Then you can also specify your optimizer, just as I was able to specify my optimizer. So in this case now, I'm not trying to say, okay, let us try and use Adam optimizer. So you can also specify the kind of loss you want to use. Loss. I'm trying to use categorical cross entropy. Come on. So it's unable to connect to runtime. Oh, I understand. All right, so don't let us waste too much time. Let's just see what happened. Let's just see the results. I'm having issues with okay, so after training it in Keras, so you just have to do is to your dense, specify the number of neurons, number of inputs, the second dense. You just keep adding the layers, and then the output, which is softmax. And you specify the optimizer, your loss, and then the metric you want to use. All of this we've done by coding from scratch in TensorFlow. So you can just import to categorical instead of hard coding it the other way I did it. You can just Keras has that way of how you can do that instead of hard coding it the way I did it. Create a function to do that. So I have this. Then I was able to fit the model, and then when it started with 73, and then 79, and then when it was done training, 78. So you can actually increase this number of epochs to whatever number. This is just to actually make us see how this thing works. Now one reason why I'm actually adding this is now parameter hypertuning is very, very important. You don't just want to be building a neural network that keeps adding the network, or it just keeps doing this or doing that. You want to be able to have an optimized neural network that is optimized for a particular problem. You don't want to just be applying this, just say, okay, 1000 number of neurons in H1 before sitting layer, or the 3000 in the last layer. You don't just want to be adding all these things. You want to know what is the best number of neurons for this particular layer. What's the best number of neurons for this particular layer? What's the best number of optimizers for this particular problem? What's the best loss for this particular problem? So that's why I actually wrote a network parameter hypertuning. I'm also going to be sharing that with you, so you can actually see all of these things, how I was able to tune the network to be able to give me optimal parameter. And so when I tuned the network, it told me that the best. Now, okay, let me start this. This Titanic classifier was the script written to help me tune my network. Was a script written to help me tune my network so that I can be able to so that I can actually have an optimal value of the H and then the H2, the optimizer choice and the likes. So, and I also added okay, it takes in the data you wanted to learn from, the number of epochs, the batch size, and the learning rate, and then the validation data. which you want to use to test. Then I also did it such that theta.layers you can actually add the number of layers. I've defined the layers already, so I want it to make choices of all of these layers and then give me the optimal value for H1 and then the optimal value for H2. Do we get it? And the same thing for optimizers. So all I do is, okay, this is the way I add my layers to the class, to the parameter appertuner. So I called it a turning classifier. So parameter appertuner. So I added it layers, then optimizers, added it that way. So that's the way it works. And it told me, okay, the best optimizer I can use aside from RMS prop, Adam, and graded descent, it tells me, okay, the best optimizer is RMS prop, and then the best hidden number of neurons for hidden layer 1 is 50. The best number of hidden layers for 2 is 200. You can actually try to expand and put more and more of all of these things, and then run this thing on Colab, and then change your runtime. Oh, my internet is fluctuating. All right, so you can just keep running this over and over again, and then you're gonna have the best. Okay, you're gonna have the best. Now let's go back to the best results. Let's go back to slides. All right, so we've been able to see. Oh, all right, so let me see. Let me set up my. Alright, so we need to pull all of these things together, model parameter appertuning neural networks. So Tensorboard, we've seen how it works. So Tensorboard gives you the flexibility of visualizing your training parameters, metrics, or any statistics in our neural network. And it's a tool for providing the measurements and visualization needed during the machine learning workflow. So Tensorflow is very, very good for visualizing your neural nets. So Tensorflow can take in scalars. I've mentioned all of this, distribution, input data, in form of images, audio, text, or whatsoever. We get it? So these are reference materials. I'll be sharing this collab. I'll be sharing this notebook. I'll be sharing this reference. I'll be sharing the notebooks. I'll be sharing the link to my GitHub regarding all the codes, and I'll also be sharing the links to all the Medium articles I've written that will help you that will explain losses, optimizers, how you need to make your choices of optimizers, and so many other things like that. So I'll be sharing everything immediately after this video. So I want to believe you guys have been able to learn a lot. You can actually reach me. Via email. You can reach me on Twitter. Just if you have any issue, try and reach me regarding Tensorflow. I'm always here to help. So I want to say thank you very much for listening to my awesome session. I want to believe you guys have a lot. You've been able to learn a lot. So thank you very much and stay blessed.
Data science, it's been amazing because I attended a 5 weeks lecture. I started with Dr. Bayo when he was explaining the basis of data science, supervised learning, unsupervised learning, and all those machine learning, artificial intelligence. He was explaining the use of data, and aside that, I also attended Big ML class. Big ML class awesome because you can predict. I understood the difference between precision and accuracy. So I understand that data must be precise than accurate because precision is a better one. I also understood Power BI and sentiment analysis, Big ML majorly. It has been my own major takeaway, and the lectures were so broken down such that anybody can understand it, and it has been amazing. So I would recommend anybody to take this class, anybody regardless of their field. I just think you can come, and when you take the class, I'm sure that we have pretty good lecturers. The most amazing part of the lecture was analyzing coronavirus. Yeah, it's so updating here.